just confirm what astronomers suspected. It vastly expanded the scale and complexity of what the universe could be, reshaping our comprehension of space, time, and cosmic evolution. Before we start, smash the like and subscribe buttons for more updates. From its initial observations, Webb unveiled a vista of the universe that was not only more densely populated with galaxies than previously imagined, but also far more chaotic and dynamic. Where earlier telescopes detected faint, blurry splotches of light from distant objects, Webb produced detailed high-resolution images revealing tightly packed clusters of galaxies, intricate structures within stellar nurseries, and ancient light traveling for billions of years. These revelations weren't just aesthetically magnificent. They carried immense scientific weight. Webb revealed galaxies that had formed surprisingly early in the universe's history, some existing just a few 100 million years after the Big Bang. This discovery alone forced scientists to rethink theories about how quickly and efficiently matter can coalesce into organized structures. The implication of seeing these early galaxies was profound. It suggested that the conditions necessary for star formation and galaxy assembly might have occurred far more rapidly than previously believed. The telescope detected galaxies with well-defined spiral structures, galactic bulges, and even dust elements previously assumed to take much longer to develop. This meant that the processes leading to cosmic complexity were either much faster or fundamentally different from current models. Moreover, the presence of supermassive black holes at the centers of some of these young galaxies presented further questions. How could such massive entities form so early? Their existence challenged conventional timelines and hinted at unknown mechanisms of rapid mass accumulation. In May, Webb detected the farthest known black hole merger within the galaxy system, 740 million years after the Big Bang, suggesting a fast growth rate for black holes through mergers even in the young universe. Another astonishing revelation from Webb's early imaging campaigns was the sheer scale of the observable universe. Regions of space once thought to be relatively empty were shown to contain entire fields teeming with galaxies, stars, and matter in transition. With a mirror more than 6 times larger than Hubble's and sensors attuned to infrared, Webb captured light that had traveled over 13 billion years. This ability to observe the cosmos at such extreme distances provided not only a direct look into the universe's infancy, but also a panoramic perspective on its vastness. Each point of light Webb resolved wasn't a single star, but often an entire galaxy, each containing billions of stars and likely countless planetary systems. In June 2025, astronomers unveiled Webb's largest view yet of the early universe, a richly detailed catalogue of nearly 800,000 galaxies from the Cosmos Web Survey, covering a patch of sky equivalent to 3 full moons side by side. The scale of what Webb was revealing extended beyond just distance and age. It hinted at the deep richness of cosmic diversity. It found galaxies of strange shapes, some stretched and twisted by gravitational interactions, others oddly compact and still more forming in bizarre configurations that defied neat classification. These galaxies weren't uniformly distributed either. Some regions appeared to host vast cosmic webs of matter, filaments of gas and dust connecting clusters of galaxies across hundreds of millions of light-years. These filaments provided a tangible view of the large-scale structure of the universe, mapping the scaffolding around which galaxies and dark matter coalesced. Within our own galaxy, Webb's vision penetrated dense molecular clouds to expose the earliest stages of star and planet formation. It imaged protostars still shrouded in the gas of their birth, tracing outflows of material, jets, and shock waves that shaped their surrounding environments. In regions like the Carina Nebula, the telescope uncovered exquisite details of turbulent stellar nurseries, showing massive stars in the act of carving out cavities in space with their radiation and winds. This resolution allowed scientists to study stellar evolution with unprecedented granularity and build models that more accurately represent the life cycles of stars. A new 3D visualization of the cosmic cliffs in the Carina Nebula released in May 2025 helped the public comprehend the 3-dimensional structure of these star-forming regions. But perhaps the most humbling consequence of Webb's discoveries was the recontextualization of Earth's place in the universe. By revealing that the early universe was not only teeming with galaxies, but also complex in ways never predicted, it emphasized the enormity of cosmic history and the relative insignificance of our planetary perspective. In just one small section of the sky, what might appear to the naked eye as an empty patch turned out to be a bustling sea of galaxies. This realization deepened the understanding that our observable universe is merely a sliver of an even greater, potentially infinite, reality. Further observations from the telescope included spectroscopic analyses of exoplanet atmospheres, detecting molecular fingerprints like water vapor, carbon dioxide, and methane in distant worlds orbiting alien stars. These detections, while not direct evidence of life, open new pathways in the search for habitability beyond Earth. In June 2025, Webb directly imaged its first exoplanet, JWST, a gas giant roughly the size of Saturn, orbiting a star 110 light-years away in the constellation Antlia, marking the lightest exoplanet yet seen using direct imaging. Webb's sensitivity to subtle light differences allowed it to characterize atmospheric compositions with far greater detail than ever before, helping to narrow the focus on which exoplanets might be worth closer study in the future. The telescope also captured gravitational lensing events with extraordinary detail, using massive galaxies and clusters as cosmic magnifying glasses to observe even more distant objects. These natural lenses helped amplify the light from early galaxies, enabling astronomers to study structures otherwise too faint to detect. In doing so, Webb not only extended its own reach but provided crucial data for understanding dark matter, as the bending of light by gravity revealed where unseen mass resided. These observations supported existing models of dark matter's role in shaping the cosmos while also prompting new inquiries into its true nature. Observations of the Bullet Cluster in 2025 delivered highly detailed images showing a greater abundance of extremely faint and distant galaxies than ever before. Another key area of revelation came in the form of interstellar chemistry. Webb's instruments identified complex organic molecules in star-forming regions and on the surfaces of icy comets and asteroids within our solar system. These molecules are the building blocks of life as we know it, and their presence in such diverse environments supported the idea that the ingredients for life may be common throughout the universe. In January 2023, Webb discovered diverse ices in the darkest, coldest regions of a molecular cloud, unveiling icy molecules needed for future exoplanets and complex molecules as building blocks of life. The fact that these compounds were detectable across vast cosmic distances reinforced the telescope's role as not just an astronomical tool, but a bridge between astrophysics and the origins of life. The images from Webb didn't merely show more stars or galaxies. They painted a universe in motion. Galaxies colliding, stars being born and dying, gas clouds dancing through the gravitational currents of cosmic space. These scenes illustrated the dynamic, ever-changing nature of the universe. Webb's ability to capture this motion through time-lapse changes in brightness or structural evolution offered insights into how cosmic objects grow, interact, and sometimes collapse. The technological achievement of the telescope itself also reflects the scope of the project's ambition. Deployed nearly 1 million miles from Earth at the second Lagrange point, L2, Webb had to unfurl its tennis court-sized sunshield, align 18 separate mirror segments with nanometer precision, and maintain stable temperatures near absolute zero. These feats ensured its instruments could function without interference from heat or light sources, enabling the kind of precise measurement needed to explore the universe's deepest secrets. Every successful image and data stream proved not just a victory of science, but a testament to the engineering excellence that brought the observatory to life. The clarity of Webb's vision allowed it to peer into the dusty environments where Hubble's view was obscured. Dust, long the nemesis of optical astronomy, became almost transparent under Webb's infrared gaze. This allowed scientists to see the hidden stages of galactic mergers, the structures of stellar disks where planets may be forming, and even to understand how dust itself evolved in the early universe. Rather than being a nuisance, dust became a source of insight into the cycles of matter formation and destruction that govern the cosmos. With every new image and data release, the James Webb Space Telescope has peeled back layers of mystery from the universe's deepest vaults. Its reach extended so far that it effectively served as a time machine, not only looking across space, but into the earliest epochs of cosmic history. By studying the light from ancient stars and galaxies, Webb provided evidence of the first chemical elements being formed, the processes of reionization that lit up the universe after its dark ages, and the moments when galaxies first began to shine with starlight. In 2025, astronomers identified dozens of small galaxies that played a starring role in reionization, transforming the early universe into the one we know today. These breakthroughs didn't only serve scientific curiosity. They had cultural and philosophical implications. Webb reminded humanity that the universe is more ancient, vast, and active than any previous instrument revealed. It suggested that cosmic evolution is marked by incredible diversity, efficiency, and rapid transformation. These qualities, observed so clearly and on such large scales, force us to reassess our place in the tapestry of time and space. In essence, the James Webb Space Telescope didn't just show us more of the universe. It changed the way we understand its formation, structure, and scope. It proved that the cosmos is not just old, but filled with ancient intricacies that were previously invisible. It expanded the known timeline of galactic development and illustrated the speed and sophistication of early cosmic processes. In May 2025, Webb discovered the most distant and earliest galaxy, MZ14, existing just 280 million years after the Big Bang with a redshift of 14.44, surpassing the previous record holder, JWST 14-0. It revealed that the universe is not only larger than we thought, but more intricate and vibrant at every level. Every revelation from Webb is a doorway to deeper questions. Its discoveries ignite the imagination while also challenging existing paradigms. As more data is collected and analyzed, the initial glimpses Webb has offered are only the beginning. The true scale of the universe as unveiled by this telescope is not just about size or distance. It's about the complexity, beauty, and interconnectedness of everything that exists. With each observation, Webb isn't simply observing the universe, it's rewriting the cosmic story in real time, with pages that stretch across billions of light-years and epochs. As the James Webb Space Telescope pushed further into the unknown, it also began to reshape how scientists approached astronomical research itself. Previously, many observations relied on short-exposure snapshots due to technological constraints. But with Webb's power, long-duration exposures became the norm, revealing fainter objects with greater precision and enabling astronomers to compile extensive, multidimensional datasets over time. These deep-field observations uncovered transient phenomena, events that flicker into existence and vanish over days or weeks. Supernovae, flaring stars, gamma-ray burst afterglows, and microlensing events were captured with a clarity never seen before, allowing researchers to study the physics of extreme environments. Additionally, Webb's instruments contributed to understanding the life cycle of dust and gas in the interstellar medium. It tracked how material recycled between stars and space, observing dying stars ejecting matter into their surroundings and young stars gathering gas to form planets. These observations showed that the elements crucial for life, carbon, nitrogen, oxygen, are continually forged in stars, spread by stellar winds and supernovae, and incorporated into new generations of stars and planets. Webb